In this session, we are going to deal with block data transfer instructions in ARM. So, block data transfer instructions are used for multiple register load store operation, right? So, there are two types of multiple register load store operations used for block transfer. First one is known as LDM instruction. So, LDM stands for load multiple. So, what do you mean by load multiple? Let us take, you are having data memory shown as in the figure, right? These are the address locations of each location present in data memory, and this is a data corresponding to each location in memory. Similarly, here we are showing the registers. Let us take R0, R1 and R2, and these are the data present in these registers. Initially, let us consider that all the three registers are having data as 000, and let us consider that location 4000 is having a data 101010, 40004 is having another data 202020, and 4008 it is having another data 0008, right? On this we are going to apply load multiple instruction. So, load multiple means what? It is used for loading block of memory contents to corresponding registers, right? Data present in a block of memory will be moved on to corresponding register. So, let us take, I am initializing a pointer to 4000 location. So, the content of 4000 will be moved on to R0. Then the pointer will be automatically incremented to next location, that is 4004. Content of this will be moved on to R1. Again, the pointer will be incremented to 4008. Content of that 4008 will be moved on to R2, right? So, corresponding locations of memory will be moved on to corresponding registers. So, 400 location content will be moved on to R0, 4004 location content will be moved on to R1, etc. So, here what you are doing is you are moving a block of memory content to corresponding registers using LDM instruction. Similarly, in the case of STM instruction, what do you mean by STM? It is store multiple. So, in the case of store multiple instruction, a block of register content, that means multiple register content will be moved on to corresponding memory addresses. That means content of R0 will be moved on to memory location 4000. Content of R1 will be moved on to memory location 40004. Content of R2 will be moved on to memory location 4008. So now you can see that whatever data was present in registers, it is moved on to corresponding memory location. This is a function of load multiple and store multiple instructions, right? And you should keep in mind both this load multiple and store multiple will take multiple CPU cycles. It is not a single cycle instruction, it will take multiple cycles. So, load multiple, for example, it takes 2 plus n into t cycles, where n is the number of registers that is to be loaded, right? So, in this case, number of registers that is to be loaded is 3, and t is the number of cycles required for each sequential access to memory, right? T means number of cycles required for each sequential access to memory. So, whenever you are accessing the memory sequentially, T stands for number of cycles required for accessing a memory, right? So, LDM will take 2 plus n into t cycles. So, what you should keep in mind, LDM and STM will increase the interrupt latency. So, if you are using this LDM or STM in an interrupt service routine or an interrupt function, it will increase the interrupt latency. It will increase the time taken for execution of the interrupt. Next, we will see the syntax of LDM and STM instruction. So, syntax will be LDM or STM. Then, in curly braces, condition field. So, why you are using this curly braces? Because it is an optional field. Conditional code is optional field. Then, you should specify addressing mode. Addressing mode should be specified. Then, RN. Right? RN is a base register holding the address, then set of registers. So this is syntax for LDM and STM. So here you should keep something in mind. Addressing mode field is not optional. It should be added with LDM or STM. So what do you mean by addressing mode? In the previous slide we have seen that whenever you are moving the content of memory to a register, after each movement of the content of memory to a register, the address pointer will get incremented automatically. So, in what method the address pointer is getting incremented is specified by addressing modes. Right? In what method the address is getting incremented automatically is specified by addressing mode. There are 4 addressing modes for block data transfer instruction. First one is known as increment after, or short form is IA. So when you are writing LDM, how will you write? LDM IA. So IA stands for increment after. What do you mean by increment after? In the case of LDM or STM, first load operation will take place, then increment will happen. That is known as increment after. Second one is increment before. So if you are using increment before as the addressing mode, what will happen? First the increment of the pointer will take place. That means pointer will be incremented to a next location. Then only load or store will happen. Similarly, decrement after. Decrement after means what? First load or store operation will take place, then decrementing of the address pointer will take place. Finally, decrement before. That means first decrementing of the address pointer will take place, then load or store operations will happen. So these are the 4 addressing modes available for LDM or STM. Right? So increment after means first the load or store operation will happen, then address pointer will increment. Increment before means first of all address pointer will increment, then only load store operation will take place. So increment after means increment will take place after the load or store. Increment before means it will increment, then only load store will happen. That means increment will take place before the load store. Right? Then let us see some examples. So one of the example, it is like this: LDMIA R0 exclamation in bracket R1 R2 R3. So these are the register list. R0 is the register holding the base address, and this is LDM with an addressing mode IA. So LDM IA means content of address location pointed by R0 will be moved on to R1. Then content of address location pointed by R0 will be incremented by 4. Content of that incremented location will be moved to R2. Again the address location will be incremented by 4 and content of that incremented location will be moved on to R3 in a sequential manner. Right? And this can also be written like this: LDMIA R0 exclamation bracket R1 hyphen R3. So this hyphen shows, what does it show? It shows the range of registers. So hyphen means R1 hyphen R3 means the register list will be containing R1, R2, R3. Right? That is shown by hyphen. So both these are same. Similarly, you can use LDMIA R0 exclamation R1 hyphen R3 comma R5. That means you are combining these two types of register list representation. So what does it mean? Here the register list contains R1, R2, R3 and R5. So here you are combining both these. And this is where you are incorporating STM as the instruction. So STMIB R0 exclamation R1 hyphen R3. So what does it mean? First incrementing of the pointer will take place, then to that incremented address content of R1 will be stored. Then again the address location pointed by R0 will be incremented, to that incremented address R2 will be stored. Again incrementing will take place and to that incremented address R3 will be stored. Right. So these are the examples of LDM and STM instructions. Then this provides a complete list of LDM and STM instruction using this 4 addressing modes. So STMIA operation stands for store multiple increment after, and the corresponding load operation will be like this, LDMDB. So LDMDB is the opposite of STMIA, right? So this provides a complete list of all the operations. Next we will see one example for multiple register load store, and addressing mode is increment after. So let us take, this is your data memory with the corresponding address. Then these are the set of registers with the corresponding data. So initially all the registers are having data as zeros, and here each register, each memory address is having corresponding data. So here 4000 is having a data 10101010, 4004 is having 202020, 4008 is having 003, etc. Right? So now I am writing an instruction LDR R0 comma equal to 0x4000. What does it mean? This address location 40004 or this constant will be moved on to R0. So this constant will be moved on to R0. So what does it mean? R0 is containing an address known as 4000. That means R0 is acting as a pointer to this address location. Right. Now I am writing LDMIA R0 exclamation R1 hyphen R3. So what does it mean? Here the addressing mode used is increment after. So what will be the first operation? Content of address location pointed by R0. What is the address location pointed by R0? 400. What is the content of this? 101010. This content will be moved on to first register, which is my first register R1. So this content will be moved on to R1. So R1 content will be overwritten with this data. And then since it is increment after, pointer will increment to a next location. Content of that location will be moved on to second register, which is second register R2. So this content will be moved on to R2. Then again this pointer will be incremented to a next location. Content of that location will be moved on to third register, that is R3. Finally, the pointer will get incremented to a next location. So whenever you are performing a load operation, address location or address pointer will keep on incrementing. So even after moving the last data, the address pointer will increment to the next location. So now to what location address pointer is pointing to after executing this LDMIA? Address pointer will be pointing to 400C. You should keep in mind. So after executing this instruction, R1, R2 and R3 will be having these data, and the address pointer R0 will be having this address 400C. Right? Next we will see again multiple registers load store, but here the addressing mode is increment before. Previously we have seen increment after. So let us take the same example. You are moving address location 400 to R0. So R0 is acting as a pointer. My instruction is LDM IB R0 exclamation R1 comma R3. So here instead of IA in the previous instruction, here I am using IB. So since it is increment before, what will happen? Before moving the data to R0 or the corresponding register, address pointer will increment. So before performing the load, incrementing of address pointer will take place. That is known as increment before. So you can see that address pointer was initially pointing to this. Before performing load, it will increment to 4004. So now the address pointer is here. Address pointer has been incremented to 4004. Then content of that address pointer will be moved on to R1, right? So in the previous case, the first content was moved on to R1, but here address pointer will increment to a next location and content of this location will be moved on to R1. Then again the address pointer will increment to a next location, content of that will be moved on to R2. Again it will get incremented to a next location, address pointer pointing to the data pointing to that address location will be moved on to R3, right? So here what is the difference between increment after and increment before? In increment before performing load, incrementing of address pointer will take place. That means first address pointer will be incremented to 4004, then only the movement will take place, right? Again it will increment, movement will take place. Like that it will keep on going on until the last register is getting the data, right? So after executing this instruction, the corresponding registers will be having corresponding data. And what will happen to address pointer R0? It will get pointed to 400C, because now you can see address pointer is pointing to this location. So it will be updated with the 400C, right? Any doubt? So this is regarding with the increment before addressing mode. So now we are going to deal with decrement after. Till now you are dealing with increment after and increment before. That means the address pointer will be incrementing, but now we are going to deal with the operation where address pointer is getting decremented. So first operation is decrement after. So here I am writing an instruction LDR R0, 400C, right? So what will happen? This 400C location will be moved on to R0, and here you should keep in mind the address location is getting decremented, because the initial location is 400C, then it is 4008, 4004, 400. So address location is getting decremented in this example. So I am writing an instruction LDM DA, that is LDM decrement after R0 exclamation R1 hyphen R3. So what does it mean? Here it is DA, that means decrement after. So the address location pointed by R0, that is content of 400C, will be moved on to R1, right? After this move operation is complete, what will happen to address pointer? Address pointer will decrement to 4008, because here the address location is decrementing. That is the main difference. That is why it is known as decrement after. So address location will get decremented to 4008. Then the corresponding that data will be moved on to R2. Again address pointer will decrement to 4004. That data will be moved on to R3. Again address pointer will decrement to 4000, right? So after each load operation is complete, address pointer will decrement instead of incrementing in the what you have seen in the previous case. So that means after the last load operation is completed, again it will get decremented. So what will be the final value of R0, or R0 will be pointing to which address? 4000. So the final address will be 4000 stored in R0, right? So this is how LDMDA is working. Next we will see decrement before, right? We have seen increment before. So increment before, what does it mean? First the address location will increment, then load or store will happen. Here first address location will decrement, then load or store will happen. So again you are moving the address location 400C to R0, right? I am writing LDMDB, decrement before R0 exclamation R1 hyphen R3. So what does it mean? Since it is decrement before, address pointer will decrement first. It will decrement before the load or store operation is done. So it will decrement, then the data present in that location will be moved on to R1. Again the address pointer will decrement, the data present in that location will be moved on to R2. Again address location will decrement, address pointer will decrement, the content of that address location will be moved on to R3, right? So what will be the final address pointer? It will be pointing to 4000, right? So this will be the address location after executing LDMDB, right? So this is how you are dealing with load multiple. Next we will see store multiple instruction. For example, I am taking decrement after, right? So again I am writing LDR R0 equal to 400C. That means 400C is moved to R0, and I am going to write an instruction STMDA. STM stands for store multiple. Till now we are dealing with load multiple. Now I am going to write store multiple. So store multiple means what? Content of registers will be moved on to corresponding memory addresses. The register content will be stored onto memory. It is just opposite of LDM, right? So here I am going to move the content of registers to corresponding memory location. So now you can see that your base register is pointing to 400C. 400C. Then since it is decrement after, what will happen? First store operation will take place, then only decrementing will take place. So I am going to store the content of first register to address pointer pointed by R0. So R1 content will be stored onto the address location pointed by R0, right? You can see this value will be stored onto this memory location. Initially all the values were zeros. Then the R0 memory pointer will decrement to 4008. Again to this location content of R2 will be stored. Again the address pointer will decrement to 4004. To this location content of R3 will be stored. Again the address pointer will decrement to 4000. That means after each store operation is completed, decrementing of address pointer will take place. And what will be the final address pointer in R0? It will be 4000. Initially it was 400C. After executing this, it will be 4000. Why? Because this write back is there. If this write back is not there, address pointer will be previous one itself, right? So these are the examples showing load and store multiple instructions. So next we will see that this same load store multiple operation can be used for stack operation also, right? So for time being I am going to explain this with the help of a push operation. Push operation means you are going to push the content of registers onto memory location. So stack push operation means what? Register contents will be pushed on to stack. Stack is nothing but a memory location. To that memory location you are going to store the contents of certain registers. So before going to that, we will deal with what are the different types of stacks available in ARM or any other microprocessor in general. So first of all, this is the first type of stack implementation. So here this R9 is the initial pointer, R9 dash is the updated stack pointer, right? Let us take this as a stack. So what is happening here? Initially the stack pointer was in this location, and to that location content of R0 was stored. Then the address location or address stack pointer will get incremented to the next location. How you found out that it is incrementing? Because you can see that initial pointer was in 100C, final pointer will be there in 1018. That means your address location is getting incremented, right? So after storing R0, stack pointer will increment to next location. There R1 will be stored. Again it will be incremented to next location. In that place R5 will be stored. Again it will get incremented, and it will be the updated pointer will be pointing to this empty location. So what is this type of stack implementation known as? This is known as empty ascending stack. So first of all, why it is known as ascending stack? Why it is ascending stack? Because you can see that whenever the address pointer is changing, the address location is getting incremented. So since the address location is getting incremented, it is known as ascending stack. And why it is empty ascending? Because the updated pointer is pointing to a location which is empty, which is not having a data, right? So since the address location is getting incremented, it is known as ascending stack. And since the updated pointer is pointing to a location where no data is there, or it is pointing to an empty location, it is known as empty ascending stack. So next one is the opposite of that. So here, what is this type of stack known as? Whether the address pointer is incrementing or decrementing. Here also address pointer is incrementing. You can see here it is 100C, and in updated pointer it is 1018. That means address pointer is incrementing here also. But what is the difference? The updated pointer is pointing to a location where data is present. So it is known as full ascending, right? So in full ascending, how the operation is happening? Initially R9 will be pointing to this location, right? So before moving the data, the address pointer will or stack pointer will increment to the next location, then the data will be moved. That means increment will take place, then only the push operation is taking place. Again incrementing will take place, push operation will take place, right? That means before push operation is implemented, incrementing of the pointer will take place in full ascending. But in the case of empty ascending, what is happening? First push operation will take place, then only incrementing will take place. First push operation will take place, then only incrementing will take place, right? So so why it is known as full ascending? Why it is known as full? Because updated pointer is pointing to a location where data is present. So that is what is known as empty ascending and full ascending. Next one, what is this? What is this known as? Whether the address location is incrementing or decrementing. How will you see that? You can see that initial pointer was here, updated pointer is here. That means whenever we are changing the pointer, address location is getting decremented. Initial pointer was there in 10C, updated pointer is there in 100. That means address pointer is getting or stack pointer is getting decremented. So this is known as descending stack. And what type of descending stack? Empty descending. Why? Because updated pointer is pointing to an empty location, right? So this is an example for empty descending stack. So here what is happening? First the push operation will take place, then only the address location or the stack pointer is decrementing. First push will happen, then stack pointer will decrement. In the case of empty descending. Then the last one is, here also you can see address pointer is getting decremented. You can see initially it was in 10C. Now the updated pointer will be in 100. So address pointer is getting decremented. So it is descending stack again. And what type of descending? Full descending. Why? Because updated pointer is pointing to a location where data is present, or it is pointing to a location which is full of data. So these are the 4 different types of stack available. So next we will see what are the store instructions applicable for each type of stack. So for empty ascending, what is happening? First store operation will take place, then incrementing will take place. First store, then incrementing. So what is it known as? What type of addressing mode you should use here? Increment after. So first store, then increment. So it is increment after. So you should use STMIA. Store multiple increment after. Then what will be the base pointer? It will be base pointer will be R9. And which all registers you are moving? R0, R1, R5. So what does it mean? What is meant by STMIA? What does it mean? R0 content will be moved on to address pointed by R9. Then address location will be incremented. To that location R1 content will be stored. Then again it will get incremented. To that location R5 will be stored. Again the address pointer will be incremented to this location, and here no data will be there. So STMIA is used for empty ascending. Then for full ascending, STMIB is used. Why IB is used? So here you can see that first incrementing of address pointer will take place, then only push operation or store operation is taking place. So STMIB is used. That means first address pointer will increment, right? Then R0 content will be stored onto address pointer pointed by R9. Then again it will be incremented, R1 content will be stored. Again it will be incremented, R5 will be stored. So here first incrementing of address pointer or stack pointer will take place, then only store operation is taking place. That is why STMIB is being used. So next we will see empty descending stack. So for empty descending stack you are using STMDA, that is decrement after. That means first push operation will take place. That means content of R5 will be pushed on to address location pointed by R9. So content of R5 will be pushed on to address location pointed by R9. Then decrement will take place. That is why it is known as decrement after. Address pointer will decrement after the push operation. Right. In the case of full descending, you are using decrement before. That means the address pointer will be decremented first, then only the push operation will take place. That means decrementing will be taking place before the push operation. So first R9 will be decremented from 100C to the next location. Then R5 will be stored onto that location. Again it will be decremented. Then R1 will be stored. Again it will be decremented. R0 will be stored. Right. So this is how store multiple instruction can be used for implementing push operation on different types of stack. Similarly, load multiple instruction can be used for pop operation. Pop operation means the register content will be, what will happen to the register content? Register content will be stored with the content of memory location. That means whatever content is present in the address location pointed by R9 in this case will be stored onto corresponding registers. So whenever you are going to load the content of memory to a register, you will be using load multiple. So for push operation you will be using store multiple. For pop operation you will be using load multiple. So next we will see the relation between block transfer instructions and the stack operations. So block transfer instruction we have seen, it is example is STMIA, LDMIA, STMDA, LDMDA, etc. And stack operation, what will be the stack operation? It will be related with the stack. That is, for example, it will be like this: STMFA, STMEA, LDMEA. So what do you mean by STMFA? FA stands for full ascending, EA stands for empty ascending, ED stands for empty descending, FD stands for full descending, right? So STMIB is doing the same operation of STMFA, right? So for easiness, if you are performing say the stack operation, either you can use STMFA or STMIB. So what does it mean? STMIB is used for implementing stack operation on full ascending stack, right? Similarly here, if you are taking STMIA is used for performing operation on empty ascending stack. So STMIA and STMEA is same. So this table shows how the block transfer instructions and stack operations are related, right? So in each block, so this is corresponding to full ascending stack. So this same block is corresponding to increment before. Similarly, this is corresponding to empty ascending stack, and it is corresponding to increment after. So these two operations are performing the same operation. So this table shows the relation between these two operations. Thank you.